Yeah, so in the last lecture or the last semester, you have been to the derivatives. Okay, so basically we'll start from the basic thing. Okay, so derivative will come. Okay, now the first thing that we need to understand is uh, derivative. If we think of, then it's a limit. Okay, but what kind of limit it is going to be? Okay, so first we need to understand the limit of the function. Okay, so let us think of the limit of function. Okay, now we need to understand what is the limit of the function. Okay, so basically when we think of the limit, we try to define when the left limit exists and the right limit exists, and if the value of this left limit is same as the right limit, then we say that the limit for the function exists and it is something or some constant. Okay, so how do we write it? So most of the time what we do is we remove or we forget about the if part. Okay, which are the necessary conditions, and then we think of only the formula. Okay, so we should not know only the formula, but we should know the formula completely. Okay, so it should be like thoroughly we should think of the formula. Okay, so let us see what we have, and we should know all about the formula as well as all about that concept. Okay, so let us think of this. So when we say the function has a limit, okay, so suppose I have a function. So let f of x be the function of x. Okay, so this f of x is a function of x. Okay, then what do we say? The value L, okay, is said to be the limit of x as x approaches to a. If, okay, so what happens so that we say this is going to be the limit? Okay, so here if we consider this, if there exists a small number epsilon greater than 0 for every delta greater than 0, such that
Sir, sorry to interrupt. Actually, I was
yes,
connected from past 5 minutes. We are starting with the syllabus, right?
yep, yes. Is there any doubt?
No, no, sir. No, sir.
Okay, okay. So that's why I'm starting with the very base. We have not yet touched the syllabus. Okay, we are just revising few concepts that we need. Okay.
Sir, what is that epsilon?
Epsilon
belongs
is a small number. Okay, epsilon
number.
is a small number greater than 0. For every small number, this delta is also a small number greater than 0. Okay, such that if I consider the difference between f of x and L, okay, the value of the function and L, it is always less than epsilon for every value of x when it is closer to a, or when the difference between x and a is going to be very small, then the difference between the value of f of x and the point L is going to be very small. Okay, or usually we write this as limit x tends to a, f of x is equal to L. Okay, this is the way you might have seen it most of the times. Okay, but actually what it means like this. If we see this graphically, okay, so what happens if we see this graphically? Okay, we have a real line. Okay, this is x-axis, and we have the another real line. So this is usually we say y-axis. This is origin, and now we have the curve. So this is any curve f of x. Okay, and now we have a point A here. So this is A here. So when we say x is approaching from the left, then we say this is limit x tends to A minus. And when we have the x approaching from right, then we say this is limit x tends to A plus. So it is coming from A plus. This is coming from A minus. Okay, or coming from left, coming from right. And if this difference we consider to be delta. So this is A minus delta and this is A plus delta. And now if we think of having the value of f at this point, okay, then the value of this function is always in between the small interval. Okay, and here we say this is L we want. Okay, so this exact value is going to be L. So this value is in the neighborhood, and so this point is going to be L minus epsilon, and this is going to be L plus epsilon. So the value of the function here is always going to be in the neighborhood of L whenever the value of x is in the neighborhood of A. Okay, so if we have the value of the function in the neighborhood of A, and if we consider the value of the function, then it is in the neighborhood of L. So if I have x in the neighborhood of A, then the value of the function is in the neighborhood of L here. So here x is going to be in the neighborhood of A. Okay. So x is in the neighborhood of A, that is A plus epsilon to A minus epsilon. So here we can have A minus delta and A plus delta. So x is in the neighborhood of A minus delta to A plus delta. And here L is this function value f of x is in the neighborhood of A. This is going to be L here. So this is in the neighborhood of L. So it is going to be L minus epsilon and L plus epsilon. So here we can see this modulus value. Okay, so we can have, see, this is the modulus value. So f of x is near L. Epsilon is going to be very small whenever x is near A. Okay, so if x is near A, f of x is near L. Okay, and then we say that the limit exists and the limit is going to be L. So is there any doubt in this definition?
Sir, can you
No, sir.
explain the graph again?
Graph, you want me to explain again? Okay, no problem. See, here we are having a function. Okay, so here this is going to be a function f of x. Now I am considering a point A. So we want to see that whether the limit at A exists or not. So this is a point A. And then you can see x is in the neighborhood of A. And what is the neighborhood we have chosen? Delta. Delta is a very small number. Okay, so A minus delta and A plus delta. So if I consider this equation, okay, so what this equation is going to be, see, x minus A is less than delta. So if I write this x minus A, then it will be less than delta, and this will be greater than minus delta. So I can write this as A This we can have as a minus delta is less than x less than a plus delta. Okay, so using this equation, we are able to get the interval that x is in the interval a minus delta to a plus delta, and this is the interval that I have noted here. Okay, so a minus delta and a plus delta. So x is in the delta neighborhood of this a. And now the same thing for this f of x. So f of x, this minus L is less than epsilon and greater than minus epsilon. So this L minus epsilon less than f of x less than L plus epsilon. Okay, so this is L plus epsilon. So I have noted the interval for f of x here. It is L minus epsilon to L plus epsilon. And you can see this is very close to L. This is going to be L. At A, it is going to be nearby L. Okay, so whenever x is in this interval, okay, whenever x is in this interval a minus delta to a plus delta, at that time f of x is in this interval L minus epsilon to L plus epsilon. This is the meaning of this graph, or this is the meaning of this statement which I have geometrically drawn here. Okay, and that's what we can say. And if these conditions are satisfied, then we say the limit of the function exists, and that limit is going to be L. So is that okay now?
Yes, sir. Thank you.
Okay, welcome. Okay, that's good. Okay, so we got
Sir,
this.
you will
Yes,
share the PDF on the group now.
pardon?
Sir, you will share the PDF of this group.
Obviously, I'll share, no problem. Okay, I'll share that. Okay, so limit is clear.
Yes, sir.
Clear.
Okay, that's good. Okay, then when we think of the limit, okay, so we test the continuity of the function. Okay, now when we test the continuity of the function, again we have to use the limit. Okay, so there is a minor difference between the limit and the continuity. Okay, and that we need to understand perfectly. Okay, so most of the students get confused between what is limit exactly and what is the continuity, or how do we test the continuity of the function. So I hope you are also writing with me. Please do writing with me. Okay, so keep on writing whatever I'm writing here. Okay, so now can any of you tell me what is going to be the continuity? Just raise the hand and then I'll ask. Okay, that's great. Okay, yeah. CS Srish Khaina.
So it's Rish Khairkar.
Okay, Srish Khairkar. Yeah.
So the point where both the left hand limit and the right hand limit exists
Hmm.
is the point of continuity.
Okay, you shared the limit again. Okay, no problem. We'll improve. Gaurav, Gautam. Yes, Gaurav. Yeah, Jay Sen Shah.
So there should be no break in the function. That's continuity.
Okay, there should not be break in the function. That's continuity.
For every value of x, there should be a value of y. I say that, and like, yeah, it should not break. I say it should be a continuous line.
Okay, that's good. That's good. Okay. Next, Vivek Farne.
LHL must be equal to RHL must be equal to limit, and all this must be a finite value.
Okay, okay, it's good. Okay, great. Okay. Yes, Chaudhary. Yes, yes.
L positive of A equal to L negative of A equal to f of x, f of A.
Yeah, that's
Simply
good. That's good.
Continuity.
Okay, that's great. Okay. What about Drashti?
Sir, so the value of the function should exist for like in the neighborhood, in the small neighborhood of x.
Okay.
Uh,
Yes.
Sir, there should not be any abrupt change or a sharp point in the
Okay.
curve, and the curve should not have any gap or any lack of point.
Great.
No,
Great.
sir. No. Oh, yeah. There can be a
Okay.
sharp point. No, that's only for differentiation, not continuous.
Very good. Very good.
Yes,
Okay.
yes.
Exactly.
No differentiation.
So let us think of one definition I got. Okay. See, the limit is existing. That's great. Okay. But the limiting value should be a function value. Okay. So here in limit, the limit value is some constant. Okay. So limit is approaching to some constant in the limit definition. In the continuity is what? See, this L should be the function value. Okay, if this L is going to be the function value, then this definition is going to change to the continuity. Okay, so good. All of you have done a good work. Okay, so good job. Yes, now we'll write the definition of continuity. So we'll go for continuity of function. Okay, so we can write here, okay, the function f of x is said to be continuous at x is equal to a if, okay, again, as I said, we most of the times forget about the if part. So this is very, very important. If for every epsilon, epsilon is a small number now. Okay, for every epsilon greater than 0, there exists a delta greater than 0 such that mod of f of x minus f of a is less than epsilon for every mod of x minus a less than delta. And that's what we say. This is limit x tends to a, x is approaching to a, and then we have this f of x is equal to f of a. So f of a is the function value of this function f of x at the point a. Okay, and when this function takes the function value as the limiting value, okay, so its limiting value and function value is going to be same. Okay, so you can see as earlier in the limit, it was going to be a constant L. Okay, so in limit, it approaches to a constant point L. In continuity, it approaches to the function value. Okay, there's a minute difference that we need to understand. Okay, so here, the function value, when we say the limit exists, that means left limit and the right limit. Okay, so the left limit and right limit both approach, they are finite. Obviously, when we say exist, they are finite and they approach to the function value of the function f of x at x is equal to a. Then we say the function is continuous at the point x is equal to a. Okay, so here, if we try to figure out, then this L, okay, so whatever this value L is going to be here, it becomes f of a. Okay, so it becomes f of a. So how we are able to draw the graph for this? Okay, for any function, we can have the graph like, so we have, this is x-axis, this is going to be y-axis. Okay, this is the origin, and you have any function. So this is f of x. Okay, and we have a point a here. So the interval a minus delta. Okay, a minus delta. This is a plus delta. Okay, and then if I consider at this point. Okay, so this is a point, and this point is exactly f of a. Okay, and if we consider this intervals, so what happens to this interval and what happens to this interval, then this value for this delta neighborhood of a is, this is going to be f of a plus epsilon, and this is f of a minus epsilon. Okay, so the value of the function, okay, here this is going to be f of a exactly. Okay, so if we consider the delta neighborhood of this a, then we get the epsilon neighborhood of f of a. Okay, the value of the function at this point a. Okay, and here x may come from this side or x may come from this side. So whether it is the left limit or the right limit, it always approaches to the function value of this f of x at this point a. Okay, and if it approaches to the function value, then it is going to be the continuity. Okay, so is there any doubt in continuity?
No, sir.
No, sir.
No,
Can you
sir.
please
No, sir.
repeat the last statement?
No, sir.
Okay, so here what we got in the continuity, whenever I have the value of x in the delta neighborhood of a, then I will have the value of f of x as in the epsilon neighborhood of a. Okay, so that means if x is here or here, the value of f or the limiting value will be nearby this f of a. Okay, so as x approaches to a, f of x will approach to f of a. Okay, this is the continuity. Okay, so any doubt?
Sir, can you please explain the difference between continuity and limit again?
Yes, very good. Okay, so what is the limit? You got here, you can see in the limit, we are having a constant value. Okay, we are getting a value L, no? Are you getting this limit? We are getting a value L, right?
Yes, sir.
Yes.
sir.
Okay. So this L does not depend on f of x. Okay. In the limit, whatever the value we are getting L, okay, it is independent of this f. Okay. And in continuity, what is happening? See, this limiting value is depending on f of x, no?
Yes, sir.
So this is the minor difference. Okay. That in limit, we get a constant value L. So every limit is approaching to that value. Okay. But here in continuity, it is approaching to the function value. Okay. It is approaching to the function value. Okay. So that is the minor difference. That's what I say, the minor difference. Okay. So in limit, we are approaching to the constant point L. Okay. In the continuity, we are approaching to f of a. Okay. So the limit value is same as the function value. Here, limit value is not same as the function value. This L may be f of a, may not be. Okay. So this L may be f of a, may not be f of a. Okay. And that's why if it is not f of a, it is the limit. If it is f of a, then we can have an additional property of the function, that the function is going to be continuous. So got your doubt clear?
Yes, sir. Thank you.
Okay, that's good. Welcome. Okay, so once we have the limit of the function, once we have the continuity of the function, then it comes derivative. Okay, so then we need to understand what is going to be the derivative. Okay, so again, I'll ask you, can any of you define what is the derivative of the function?
Tangent at a continuous point.
Yeah, please raise your hand so I can ask or I can see who is answering. Okay. Okay. Yeah. Mansi,
It is the slope of the function.
it is the slope of the function. Very good. Yeah. Anand Krishnan,
Sir, slope of the line at the point.
slope of the line
Line.
at the point. Okay. Sachin,
Sir, I also wanted to say that the differentiation, matlab derivative of a function is slope only. So, matlab
okay. Slope.
yeah.
Okay, no problem. What about Man?
Sir, tangent at any continuous point.
Yeah, tangent at any continuous point. That's good. Okay. But is it related to, yes, yeah,
So it is f dash x is equal to f of a plus h minus f of x by h, right?
okay.
So
So is it
First
related to
principle of
limit?
derivation, right?
Okay, that's good.
So
Is
there
it
must be no
related?
kinks in the graph.
Sir,
Yeah, just wait. Okay, wait. Okay, is it related to somewhere limit?
Yes.
Yes, sir. Yes, sir.
Okay, it's good. So we have seen the limit, we know the continuity. Now we'll try to define the derivative. Okay, how do we get the slope? Okay, and how do we get these things? Okay, so let us try to have the derivative of function. So let us try to have the derivative of the function. Okay, is it possible? What will be the function here? So we need to define a function. So suppose f of x be the function of x. Okay, so first we need to have the function. Okay, so please unraise your hand now. Okay, so you can lower down your hands. Okay, so suppose this f of x is going to be a function of x. Okay, and now I have a point where I need to have the derivative. Okay, so the function f of x is said to be differentiable at x if. Okay, so what is that condition we have? So the condition we have is limit h tends to 0 f of x plus h minus f of x upon h. Okay, or and then the important thing is that it exists. All of you, please mute yourself. All of you, please mute yourself. To the participants. Yeah, so whenever necessary, then only unmute yourself. Okay, otherwise, please mute yourself. Okay, so the condition is that, okay, this limit is called the derivative provided that it exists. Okay, so here we can have provided that, okay, it exists. Okay, so that's why I have asked you to raise the hand so we can you can only unmute yourself and then you can talk. Okay, so here this limit plays an important role, and then we call this as the first principle also. Okay, we call this as first principle also. And then there are several ways to denote the derivative. Okay, so up to it, you might have seen some notations. Now we'll introduce some more notation. Okay, so is the definition of derivative clear to you? You can say yes, no.
Yes, sir.
Yes, sir.
Sir.
Okay,
Yes, sir.
Yes, sir. Yes, sir.
okay, that's good.
Yes, sir.
Sir, provided that it exists means the limit should exist, right?
Yes, yes, definitely. If limit exists, then only it is going to be derivative. If limit does not exist, that means the left limit is going to be different than the right limit, then we say it doesn't exist. Okay, so for example, a very famous example, you might have also studied this. So if we consider the function, okay, is going to be mod x. Okay, so if I define f of x is equal to mod x, okay, then what is the left limit? It is going to be 1. What is about the right limit is going to be -1 if I want to test at 0. Okay, so left limit is not same as the right limit. So can we say, does it exist? The limit exists?
No.
No.
No. No.
So
It's a
this
continuous
function,
function, but not differentiable.
yes, this is not differentiable at 0.
0.
Okay. If I consider x is equal to 0, then this is not differentiable at 0. Okay, so that's why the condition is very important that this limit has to exist. Okay, so if the limit exists, then we'll say it is derivative. And if the limit does not exist, then we say it is not differentiable function. So this is very easy example, easy and familiar to you all. Okay,
Excuse
so
me, sir.
yes.
Sir, H is nothing but the small interval.
Yes, H is a small entity.
Okay, sir.
Yeah, sometimes we write this as, okay, so there are several ways to write this. Dy by dx is equal to, it is going to be limit delta x tends to 0, and you'll be having delta y upon delta x. So this is very, very small change in x. So we define this in the several way now. So rate of change of one quantity with respect to the another quantity, that is also we called as derivative. But this is the original one from where we enter to the derivative. Okay, so you can see what is x actually. So what is h actually? It is the difference between this entity and this entity. So h is a difference between it is a small difference from x to s plus h. So this is the difference h. So if I consider here x, and if I consider here x plus delta x is going to be very small. And this is what it is going to be y at x plus h. So it is f at x plus h. And this is y at x. So it is going to be f of x. And if I define this delta y, then it is y at x plus h minus y at x. So this way, there are the several ways to write the same thing. Okay, so that's why basically this is the first principle which can be replicated or written in the different ways in the different scenarios. Okay, so that's why first we need to understand the base, what it is and how it works. Okay, then we can interpret in several ways. Okay, so is that okay now?
Yes, sir.
Yes,
Okay,
yes, sir.
and why it is going to be the tangent? So if I take it into the tangential way, okay, then what we can have is, see, suppose this is I have okay, I have a line, I have a curve. This is going to be a curve, and this is going to be x, and this is y at x. So this is the point. What I have, this is x plus h, and this is y at x plus h. Then what this is going to be, y at x plus h minus y at x. And here you'll be having, this is x plus h minus x. So this is nothing but the slope. Okay, so if I try to draw, it's going to be the slope, and that's why we get it into the tangential way. Okay, so got this one? Got this idea? Why we get it to the tangential way?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, that's great. Okay. Yes. Okay. Yeah. Is there any doubt or is there any thing that you have not got in the definition now? Have you got the definition?
Sir, can you please repeat that part where you compared del y by del x and dy by dx?
Okay. Okay. So fine. So what we have is we denote this as a derivative. So derivative we write as dy by dx. This is the usual notation. Okay. Then what it means? It means that if I am considering a small change in y with respect to small change in x, and this small change tends to 0. Okay, means that the value, the difference between the x is going to be very small. And then what is the corresponding change in y? Okay, so if we consider a curve and then we consider the small change in x and small change in y, and we compare this ratio and we make this change to be very small, okay, then it gives you the derivative, or the other way, it gives you the tangent at that point. Okay, and if you find the value of this tangent at that point, then it gives you the slope actually. Yeah. So basically, we should say it is a tangential curve. Okay, whatever the curve it may be. Okay, the derivative is going to be a tangential curve to the given curve, provided that it exists. Okay, otherwise, if the function is going to be not continuous at that point, and then we try to find out the derivative at that point, so not possible. Or as somebody has already pointed out, if the function is going to be pointed, okay, and then we try to find out the derivative at this point, okay, so not possible. The derivative does not exist. Okay, so got this?
Yes, sir.
Okay, that's great. That's great.
Yes, sir.
Okay, so now, as I said, we are going to have the different notations. Okay, so what kind of notations we have now? So we are very familiar with the notation that derivative dy by dx. So suppose I have, so let y is the function of x. Okay, or we write sometimes this as y of x also. Okay, so y is going to be the function of x. Here, x is going to be the independent variable. Okay, so that means x can take any values. Okay, but the y will take the values according to the value of x. Okay, so for example, if I'll write y is equal to x square. Okay, so x can take any value. Okay, but what the value of y? Y will be only x square. Okay, so y cannot take any other value other than x square. So can you identify this curve?
Parabola.
Yes, it is parabola. Okay. So is it continuous?
Yes.
Yes,
Yes.
sir.
Yes, sir.
Very good. Is it differentiable?
Yes.
sir.
Yes, sir.
Yes, sir.
Okay. So parabola is continuous at any point. Parabola is differentiable at every point. Okay. So this is the way when x is going to be the independent variable and y is going to be the dependent variable. Okay. So please mute yourself immediately if you're not talking. Okay. So thank you. Okay. So here we have x is going to be an independent variable, y is going to be the dependent variable. And so we can say that y is going to be the function of x. And now if y is going to be a function of x, and we know it is going to be continuous as well as it is going to be differentiable. Okay, so let us write how do we get the derivative of this function y, or how do we write the derivative of this function y. Okay, so there are several notations, okay, that I'm going to introduce to you now. Okay, so we have dy by dx. Okay, this is very important notation. Okay, dy by dx. Okay, so in this semester you will be learning more different types of derivatives also. Okay, so up to it, you are equipped with the derivative dy by dx, but you are going to have some more different types of derivatives. Okay, so this is the one way to write it. Okay, so the other way is to write is y dash. Okay, so we use this notation also, y dash, the derivative of first order derivative of this function y. Yeah, Jason, is there any query? Okay.
So we also say y1, right?
Yeah, just wait. I'm coming to that. Just wait. Okay. So, Man, any query? Man Cheda.
No, sir. No.
Okay, you have raised your hand, so I thought you might have any query. Gaurav, Gautam. Gaurav,
No, sir. No, sir.
then you have raised your hand, so that's why I got. Okay.
No, sir.
Okay, so please lower your hand. Thank you. Okay, so here you are familiar with this notation that dy by dx is going to be y dash. Yes. Okay, and now what the another notation that we are going to introduce here is y1. Okay, so as I can write in the dash notation, I can write in the suffix notation. So this is called a suffix. Okay, y1. So here I'll be having this y dash same as y1. So it is going to the first order differential of the function y with respect to x. And here this y is a function of only one variable x. Okay, so this y is going to be only variable having only one variable x, and that's why this is also called as total differentiation. Okay, this is also called as total differentiation because y is made up of only x. Okay, the y has only contained x, or the y x is the only variable which is contributing to y. Okay, and that's why this dy by dx is also called as the total derivative. Now, what happens if I again differentiate this dy by dx? So I'll be having d2y by dx square. Okay, so please try to understand how do we read it. Okay, so this is d2y by dx square. Okay, and then again in the dash notation, we write here, this is y double dash. Okay, in dash notation, we write it as this is y double dash, and in suffix notation, we write it as y2. Okay, so we have d2y by dx square is same as y double dash is same as y2. Okay, and now again I differentiate this. Okay, so if I differentiate this, I'll be having d3y by dx cube, and in dash notation it is y triple dash, and in suffix notation it is going to be y3. So in suffix notation it is going to be y3. Okay, so this is the third order derivative. Okay, and now we again differentiate this. So I'll be having we have differentiated the third derivative, so we have the fourth order derivative. So y dy d4y by dx raised to 4, and this is in the dash notation we use Romans. Okay, so in dash notation we use Romans. Okay, so mostly we use Roman, and this is going to be y4. Okay, now again I differentiate this. So d5y by dx raised to 5, and so this is the fifth order derivative. So we do write it like this. Okay, again I differentiate this. So I'll be having d6y by dx raised to 6, and this is in Roman. So we'll be having the again in suffix notation. Okay, so the sixth derivative here, we got the sixth derivative here. Now, what I am doing actually, I'm taking the derivative of derivative of derivative, correct? So what we were having first, we were having first order derivative, then we differentiated it, we got the second order derivative, then we differentiated it, we got the third order derivative. Then we got again differentiated it. We got a fourth order derivative. Then we again differentiated it. So what is going on? We are going on with the derivative of derivative of derivative. Okay. So this process is called successive differentiation. So this process is called successive differentiation. Okay. We keep on taking the derivative. Okay. So we differentiate the function successively. Yeah, again and again. Yeah, we differentiate the function again and again, and that's why we call this as the successive differentiation. Okay, so up to the last year, you might have gone through the first order derivative as well as the second order derivative. Now here we are going to have the nth order derivative. So n may be the larger, it may be 10, it may be 50, it may be 100. Okay, so how to find the nth order derivative, that we need to understand. Okay, so you got into the idea of successive differentiation?
Yes, sir.
Yes.
Okay,
Yes, sir.
so we are
Yes,
going to
sir.
have the derivatives, right? Okay, so now here the important thing is that if I want to know the nth derivative, okay, I must understand what I am getting. Okay, because I'll go for first derivative, I'll go for second derivative, I'll go for third derivative, I'll go for fourth derivative and fifth derivative and so on. Okay, but somewhere I need to stop. Okay, so I need to stop at n. Okay, but n means how large. Okay, so as I said, it may be 10, it may be 20, it may be 50, it may be 100. Okay, so how do we get the n? That means we have to generalize. Okay, so we have to generalize this derivative. Okay, and if we want to generalize this derivative, so we need to observe. Okay, so we need to find the first order derivative, we need to find the second order derivative, we need to find the third order derivative, we need to find the fourth order derivative. Okay, and after finding these derivatives, okay, we need to observe what is happening in each derivative. Okay, what happened to first derivative, what happened to second derivative, what happened to third, and what happened to fourth. And then after observing this, okay, we need to generalize what will happen to n. Okay, so this is the procedure to find the nth derivative. First, find few derivatives, try to understand what is happening. And once you get hold what is happening, generalize this for n. Okay, so you got this idea?
Yes, sir.
Yes, sir.
Yes,
Sir.
Jason.
Yes, sir.
Yes, sir.
Yeah,
Usually
Jason.
generalization would be in a factorial, right?
Need not necessarily always in factorial.
Like if you're deriving x raised to n.
Wait, Jason. Wait. Okay, we have not yet got to the nth derivative. Okay, so the only thing is that have you got the idea how we are going to have the nth derivative?
Yes, sir.
Yes, sir.
Okay, okay, okay. So every nth derivative will not go to factor. Okay, this is the thing. Okay, this is already after having a few derivatives, then you will understand. Okay, so this is what we are going to do in near future. So you need to wait for that. Okay, so every derivative will not go to factor. First thing, factorial. Okay, so there are derivatives which will not go to factorial. There are some which will go to factorial. Okay, so we need to understand. So first, find few derivatives. After finding few derivatives, try to understand the pattern. Okay, the second thing is that after understanding the pattern, try to write it for the general formula for n. What will happen for n? Okay, this is the way that we have to go. Okay, so let us try to have the nth derivative of some well-known functions. Okay, so first we'll try to have some well-known functions and then we'll go for the problems. Okay, so yeah, yes, if you have any query, you can raise hand and I'll ask. No problem. So up to it, you got this. Yes, Bhavya.
Sir, how would this be graphically represented?
Nth derivative.
Yes.
Okay, that's a very good question. Okay. So see, the modulus of derivative. Okay, if it is going to be less than one or greater than one. Okay, that is the thing. Okay, so actually, it's interesting concept. Okay, the nth derivative. Okay, so what is the meaning of derivative that we have seen? Rate of change, right?
Yes,
We
sir.
have seen the rate of change, right?
Yes, sir.
Yes,
Okay,
sir.
so suppose you are at one place. Okay, so yeah, you are at one place and you are driving. Okay, and then you are driving a vehicle. Okay, so imagine the situation that every time you are changing your direction. Okay, and the modulus of this change is less than one. Okay, so if there is no change, then you will go straight. Okay, if there is any change, then only you will go to left or right. Okay, now suppose we are having positive. Okay, so we are going towards right. Okay, and then if you are going to right and the modulus is going to be less than one. Okay, so if modulus is going to be less than one, what is going to happen? You are just turning inside, 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 and finally you will reach here. So what is happening at this point, at this point, at this point, at this point? Okay, these are visible. Okay, actually you are changing at a very small interval. Okay, you are changing at very small interval. So here you first change. Here was the second change. Here was the third change. Here was the fourth change. Here was the fifth change. Here was the sixth change. And this way you will go to yn. So this is actually the nth derivative. Okay, you are going towards a point and every time you are keep on changing. Okay, and as I said, if you go to the left, okay, and this is the modulus less than one. Okay, if it is modulus greater than one, then you will diverge. Okay, so like that.
The
Yes.
modulus less than one of exactly what quantity?
Rate of change.
So what's the x and y axis for this graph?
Yeah, you can draw here x and y. And this is the tangential graph. This is not the original graph. Okay, this is the tangential graph. As I said, we are taking derivative. Okay, so this is the tangential graph. This is not the actual graph. Okay.
Sir, if modulus is less than one, why is it always turning inside? I didn't understand that part.
Yes. Okay. So see, if as we have defined the notations, if it is going to be 0, then it will go straight. There is no change. Okay. And what I am doing is I'm converting it to the modulus of this derivative is going to be less than 1. Okay. So if I am converting positive way less than 1, okay, then if it is going to be 1, so the rate, see, basically what is the this derivative? It is the ratio of change of y on change of x. Is that okay?
Yes, sir.
Are you getting this? Yes. Okay. So this change, okay, if it is going to be greater than 1, then it will be an increasing function. Okay.
Right, right.
So if it is greater than 1, then it will be increasing function. If it is less than 1, then it will be decreasing function. And so that's why it is slowly coming inside.
Got it.
Okay.
Got it.
As this is the tangential graph, it is slowly coming inside. Okay. If it is a greater than 1, then it will go outside. Got it?
Yes, sir. Thank you.
Okay. Okay. That's great. Okay.
Sir, excuse me. That means
Yes.
in the second case, the y1 will be inside and yn will be outside, right?
This is the one situation that we have considered.
Okay.
Or somebody asked me what is the graphical representation. So that's why I have created a one situation. Okay. And this is the situation when I have created that the change in the direction. Okay. So it depends on the function, what the interpretation will be. Got it?
Yes, sir. Thank you.
Okay. Yes. Okay. Great. Okay. So now we'll try to find out the derivatives. Okay, nth order derivatives of some well-known functions. So here, what I mean by well-known functions, when you think of the integration of u into v, so what you do, we'll consider either isolate or light to decide what is u and what is v. Okay, so these are the 5 functions which we'll know are the continuous and differentiable. Okay, so let us think of these functions first. Let us try to understand the derivatives, the nth derivatives of these functions. Okay, and then we'll go for the general ones. Okay, or the combination of this all. Okay, so suppose we have a function. Okay, let we have an exponential function. So y is going to be e raised to ax, and then we want to find out the nth derivative of this function. This is a very easy. Okay, all of you know the derivative of this function. Okay, so Jason, can you tell me what is the derivative of exponential function? This function.
It would be y is equal to x e raised to x minus 1. But y
Okay.
dash is equal to x e raised to x minus 1.
Okay. What about Dhruv? Can you tell me what is the derivative of this function?
Yes, sir.
Just
Y
solve
equal
it, sir.
to a e to the power ax minus 1.
Okay, Narendra, what will be the derivative of this function?
Sir, y dash is equals to a e to the power ax.
Yes. Okay. So all of you got this. Correct. Okay. So you got the correct derivative. So you can lower your hands now. Okay. Thank you. So what will happen if I differentiate this? Okay. So b, the function of this x. Okay. So this is going to be the function of x. So x is going to be our independent variable and y is going to be our dependent variable. Okay. So what we can do is we can differentiate. Okay. So differentiating y with respect to x, we get. Okay. So what we are able to get is here I'll write both the notation for time being. Later on, I'll not write this dy by dx. So till you get the idea, I'll write it. So we have dy by dx as y1 is equal to a into e raised to x. Okay. So what we got here, we got y1 is equal to a into e raised to x. Okay. So that's what is our first order derivative. Okay. Now, what I'll do is again differentiating. So again, differentiating above equation. We get. Okay, yeah. Shreyas. Yeah, what is the query, Shreyas? Is there any query, Shreyas?
No, sir. Sorry, sir. I forgot to lower my hand.
Okay, Shubhada, any query? Shubhada, any query? Okay. So if we differentiate this again, what we'll get? We'll get d2y by dx square, and that is going to be here as y2. So this a is here as it is, and again we'll differentiate e raised to ax. A is going to be constant, so we can have again the derivative as a into e raised to ax. So if we simplify, what you get, y2 is equal to a square e raised to ax. Okay, so this is the second order derivative that we have got. Okay, now again we'll differentiate this. Okay, so again differentiating above equation, we have, okay, what we'll be having here? So this is d3y by dx cube, and here it is going to be y3. So we have this a square remains as it is, and then again derivative of this e raised to x. So we can have this e raised to x, and again the derivative will be having this constant. So if we simplify, what we'll be having, y3 is equal to a cube e raised to x. Very simple function to understand. So this is the exponential function that we are working with. Okay, and now I want to have the pattern. Okay, we need to identify the pattern. So that's why we are finding the first derivative. We got, yes, this first derivative look like this. We got the second order derivative. Yes, the second order derivative look like this. And we got the third order derivative also. Again, we'll go for one more derivative. Okay, so here, again, differentiating. Above equation with respect to x, we get. Okay, so what we are able to get here, the fourth order derivative. So d4y by dx raised to 4, and this is y4. So it is a cube remains as it is, and the derivative again is going to be a into e raised to ax. So we can write here, this is y4 is equal to a raised to 4, and we have e raised to ax. Okay. So now we got this 4 derivatives. Okay, so we got y1, we got y2, we got y3, we got y4. So now if we go on this way, okay, that means we'll find y5, we'll find y6, we'll find y7, and so on. Okay, so what will happen in general? Okay, so Jason, any query?
No, sir. So I thought you were asking a question. What will
Okay,
happen?
okay. Yeah, I'm about to ask. Okay, so we have to go for n. So that means we got y1. Okay, we got y2, we got y3, we got y4, and now we have to generalize what will happen to yn. Okay, so here how to identify the pattern. Okay, so here what is happening for the first order derivative? Okay, you can see for the first order derivative, I got a. For the second order derivative, I got a square. For the third order derivative, we got here a cube. For the fourth order derivative, we got a raised to 4. What will happen to the nth order derivative?
A raised to n.
E to the power n, then y.
A raised to n.
Yes, a raised to n. Okay, so that means whatever the number of derivatives we are going to have, that many a we will have. Okay, and then if we combine them, that will be the power. So here, first derivative 1 power, second derivative second power, third derivative third power, fourth derivative fourth power, and then nth derivative n power. And what will happen to this function e raised to ax?
Same.
It will remain as it is.
It will remain as it is.
Yes, great. So this will remain as it is. And this is how we got the nth derivative. Okay, so this is how we got the nth derivative. Yeah, Prajwal, is there any query?
No, sir, I forgot to lower my hand. I was just reading the answer.
Anshul? Anshul, any query?
No, sir.
Okay, so fine. Okay, so in this example, we have seen that what we have to do is we have to find the first order derivative, second order derivative, third order derivative, and then we have to see what is the pattern that it is following. And once we know the pattern, yes, we are done. We are able to find the nth derivative. And here we got the nth derivative to be a raised to n, and here we got exponential function as it is. Okay, so is there any query in this example?
No, sir.
No, sir.
Okay.
No, sir.
No,
No,
sir.
sir.
No, sir.
Okay, that's great. Okay, so you got the idea. Okay, so just go through the steps once again, and we'll go for the another example. Got the steps? Yes. Okay, great. Okay. So now we got the exponential function. Okay. So again, we'll try the another exponential function. Okay. So what do we have? Suppose y is equal to a raised to x, where a is going to be a constant. Precisely, it's a positive constant. Okay. So b, the function of x. Okay, so it's going to be the function of x. Yeah. Now we need to understand the derivatives of this, and then finally we need to calculate the nth derivative of this. Okay. So what we do now? We just differentiate. Okay. So differentiating y with respect to x, we get. Okay. So what we are able to get is y1 is equal to. Yeah, that's good. Okay. So yes, Bajaj. Yeah.
So y1 will be equals to a raised to the power x into log of a.
Great. Okay. So that's good. So it will be a raised to x, and this is going to be log of a. But remember, when we write or when we talk about this log, it is going to be to the natural base. Okay, so natural base means it's going to be log of a to the base e. Okay, so that is understood. Okay, so great. Yeah. Okay, now once we got this first order derivative. Okay, good. Okay, so once we got this first order derivative, what we can do is again we differentiate. Okay, so again differentiating. Equation with respect to x, we get. Okay, so what we are able to get is this is going to be y2. Okay, so now be careful. This log a is being put a constant. Okay, this log a is going to be a constant. Okay, yeah, Prathamesh. So what is the derivative now? Prathamesh. Prathamesh Upasni. Okay, Ved.
Sir, we will get as log a is constant, we will get again log a into a raised to x.
Yeah, good. So it is going to be log a into this exponential function. So it is a raised to x. That's great. Okay, so can we write this? So this is going to be okay. So this is y1 is equal to we can have this is log a into a raised to x. Okay, that's what we have, and this now we can write this as y2 is equal to, this is going to be log of a, this bracket square, and a raised to x. Now here the important thing that we need to understand is log of a square is not same as log of a bracket square. Okay, because this will become 2 log a. Okay, so 2 log a is not same as log of a bracket square, and that's why we have to be very careful. Okay, so here you can check this with the help of any number. So it is easy to verify that 2 log a is not same as log of a bracket square. Okay. Now this is what we got, the second order derivative. Okay, so we got here the second order derivative. Again, what we'll do is differentiate this. Okay, so again differentiate it. We get. Okay, so what we are able to get here, see, this will be the third order derivative. Yeah, and this is going to be the log a bracket square. Yeah, Yash Pagare.
Log a whole bracket cube a raised to x.
Okay, that's great. Mokshada. Mokshada.
Log a whole cube into a raised to power x.
Great. Okay, so good. You're getting into this easily now. Okay, great. Okay, so log a bracket cube and you'll be having a raised to x. Great. So again, please keep lowering your hand once it is done. Okay, so again, differentiating. Above equation. We get. Okay. Shubhada, lower your hand. Tanay, lower your hand. Okay. Yeah, Hussein. What will happen, Hussein, here?
Log a raised to power 4 whole bracket raised to power 4 into a raised to power x.
Great. Okay. So log a bracket raised to 4 and it is a raised to
A raised to
x.
power x. Sir,
Great.
do we have to write all the things like again differentiating with respect to x, or we can directly solve the problem?
Better you write. Okay. So that the reader will understand that you know it perfectly what you are doing. Okay. So just like for me, you are the reader. Okay. For me, you all students are the reader because you are reading this. Okay. So you will understand what I am doing. And when you will write for you, the reader is going to be an expert person, subject expert, or he is your examiner. So if you write this, he will understand that whatever you are doing, you know it perfectly.
Yes.
Okay, so that's why we should keep writing. Got it?
Okay.
Okay.
How many differentiations should we do?
Yes, till we get the pattern.
No,
Okay,
like
so
in
if
the exam.
yes, in examination, that's what I said. Once if you are able to get the pattern, you need to show. That's why we are writing this into steps. Okay, we are finding the first order derivative, we are writing the second order derivative, we are finding the third order derivative, we are finding the fourth order derivative, and then we are writing in general. Okay, we are writing in general so that these four derivatives are sufficient for us to identify the pattern. Okay, and that's why we are writing this, or we are calculating this four derivative. So it will be sufficient for getting the pattern. One or two derivatives are not sufficient to get the pattern. Okay, so that's why we should write at least four. Okay, and then you should generalize. Okay, so now if we continue in this way, then in general we have. Okay, so what we'll be having in general, we want to find the nth derivative. Now, so you can see what is happening. Okay, so for first derivative, we got log a. For the second derivative, we got log a bracket square. For the third derivative, we got log a bracket cube. And for the fourth derivative, we got log a bracket raised to 4. Yeah, Dhruv, what will happen to n by n?
So we will get log a raised to n into a raised to x.
Very good. So log a raised to n into a raised to x. Yes. Okay. So please lower your hand. Thank you. Okay. So here you are having the nth derivative like yn is equal to log a bracket raised to n. Okay. So we got into the log a bracket raised to n. Okay. So please go through this. Please go through these steps once again. Go through the two examples that we have seen, and if you are not getting any step, you are not getting any derivative, please raise your hand. I hope you're writing with me.
Yes, sir.
Yes, sir.
Yes.
Good. Do you have any query?
No, sir.
No, sir.
The books which we should refer.
Yeah, I'll tell you at the end of the lecture. Don't worry.
Okay.
All of you are comfortable with these steps and with the concept up to it?
Yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Sir,
Okay. Yes.
sir, will there be cases where generalization is not possible?
In which case?
Like for example, sin x.
Yeah, we have just been to one part, that is exponential function. Okay. Next, we'll be coming to the trigonometric functions. We'll be going to that also. Don't worry.
Sir, can you please scroll down?
Yeah, you want me to scroll down this? Okay. This is sufficient? Is this sufficient?
Yes, sir.
Okay. So once we are done, then we'll go for the next. Okay.
Yes, sir.
Okay.
I have done, sir. I want to just see that.
Okay. Okay. No problem. That's okay. Okay. So both all of you are done with this example, right? Okay.
Yes, sir.
Okay. That's great. So now let us go with the next. So the variable one, suppose exponential. Okay. So let y is equal to cos of ax plus b. This is the general one. Okay. So a can be 1 and b can be 0. So it becomes only cos x. Okay. A can be anything and b can be anything. So it is the general case. Okay. Suppose this is the function of x. Okay. Being the function of x. Yes, Jason, any query?
So should we also do x raised to x raised to n? Because if
Just wait, we will come to that also. So as I said, we are having exponential, we'll go to trigonometric, then we'll come to logarithm, we'll come to algebraic. So that is part of algebraic, right?
oh yeah, sorry.
When we think of x raised to n, it is going to be part of algebraic function. So we'll see one by one, don't worry. Okay. Yeah, we should not be in a hurry. We should be slowly, we'll come to that point also. Okay. Yeah. Yeah. So this is the function of x, and now we want to find out what is the nth derivative of this. Okay. So the idea is now how to get the nth derivative. First, find out first derivative, second derivative, third derivative, fourth derivative, fifth derivative, if required. Okay. If we are not able to get into the pattern, then we go for fifth derivative, and then we'll try to generalize. Okay. See, we know the derivative of cosine. So, what will be the derivative of this term?
It will
Minus
be
a into sine of ax plus b.
Arush.
y1 is equal to minus a sine of in bracket ax plus b.
Great, good. Okay, so others, please lower down your hands. Okay, so what we have differentiating y with respect to x, we get, okay, so we get y1 is equal to minus a sine of ax plus b. Okay, so all of you agree with this derivative?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Great. Okay, so now slightly we forget about this derivative now. Okay, and we think of a formula. Okay, which is very easy. Okay, so cos of a plus b. So this is cos a. Okay, this is going to be cos a into cos of B, and this is minus sine of A into sine B. Is it okay?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Now, what I'm going to do is, I'm going to put this B is equal to pi by 2. Okay. So if I'm going to put B is equal to pi by 2, what I get here, this is going to be cos of A plus pi by 2. Is that okay? And
Yes.
this is equal to cos A cos of pi by 2 minus sine A and sine of pi by 2. What is the value of cos pi by 2?
Zero.
Right? So this term is going to be 0. Okay. As we know, this value is going to be 0. Is that okay?
Yes,
So
sir.
cos pi by 2 is going to be 0. So this value is going to be 0. And we got here minus sine of A. What is the value of sine pi by 2?
1.
1. Okay. So we got here a relation. Yes. So cos of A plus pi by 2 is equal to minus sine of A. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
So that means this minus sine of A, can I write it as A into cos of AX plus B? This is AX plus B plus pi by 2.
Yes.
Yes.
Yes, sir.
Can you write it? Now this AX plus B is our A. Okay, and you can see sine of A plus pi by 2 is going to be minus sine A. So that means anytime I get minus sine A, I can add pi by 2 and convert it to the cos. Is that okay?
Yes, sir.
Are you getting this?
sir.
Yes. Okay. So this is the important formula. Okay, that I'm going to use repeatedly. Okay. So now this is going to be the important formula that I'm going to use repeatedly. Okay. And now once I have differentiated this, okay, so I forget about the remaining steps now. We got the important formula or important step. And so what to do next? Next again, I'll write this as y1. So I can write this y1 as a times cos of ax plus b. Okay, and there's going to be plus pi by 2. Okay, so this is our first derivative. Okay, next what I'm going to do is I'm going to differentiate this. So easy, we can go again differentiating above equation with respect to x, we get. Okay, so what will be y2? This a remains as it is. Okay, so this a will remain as it is. And now the derivative of this cosine. So it is going to be minus a sine of ax plus b plus pi by 2. Is that okay? Are you getting this?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Great. Okay, but what I can do is I can write this a, and this minus sine of ax plus b plus pi by 2. So this is equal to a square cos of ax plus b plus pi by 2 plus pi by 2. Is that okay?
Yes, sir.
Yes, sir.
Yes.
sir.
Correct. So whatever the angle was in the previous step, what we are going to is we are going to add one more pi by 2. Okay. And now what is the benefit? Okay. So what we got here. Yeah. So here we can write as y2 is equal to, this is a square. This a into a is going to be a square. And this is cos of ax plus b and this is 2 times pi by 2. Is that okay?
Yes, sir.
Okay.
Yes, sir.
So as we have to go for generalization, we should not be in hurry. We need to identify the pattern. Okay, so that's why be patient. Okay, so we must have the patience. Okay. Now again differentiate this. Yeah. So again differentiating above equation with respect to x, we get. Okay, so what we'll get here? Y3. So it is a cube, then it is a, and this is minus sine of ax plus b plus 2 pi by 2. Is that okay?
Yes, sir.
Yeah.
Okay, that's what we have. But we know,
Sir,
yeah, this should be a
that should
square.
be a square.
Yes,
A,
yes,
sir.
yes. Okay. So this is a square. Now it will become a cube. And this is, what this term will be? This will be cos of, okay. So we can convert it to minus sine to cos. Okay, so this will be cos of ax plus b plus 2 pi by 2 plus again you will be having pi by 2. Is that okay? Are you getting
Yes,
this?
sir.
Yes.
Yes,
Okay.
sir.
So it's being interesting now. So what we get here, y3 is equal to a cube cos of ax plus b plus we'll be having 3 pi by 2. Okay, and this is our third derivative. Okay. Now we have to go to the next. So we go for again a differentiation. So again differentiating above equation with respect to x, we get. Okay. So here what we are able to get, y4 is equal to a cube remains as it is. Again we have a, again we have minus sine of ax plus b plus 3 pi by 2. Okay. So again we can have, this is a raised to 4 now. Okay. And here we have minus sine of ax plus b plus 3 pi by 2. So can we write this y4 as a raised to 4 cos of ax plus b plus 4 pi by 2. Are you getting this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Great. Okay, so what we did here, we added 1 pi by 2. Okay, so whenever we have minus sign, what we do, we add pi by 2 to the angle and then it becomes cosine. Okay, so the simple formula that we are going to use. And now you observe the pattern. So you need to identify the pattern. So are you, just raise your hand if you are getting any pattern, or I'll suggest better you write down and then you can tell me. So in general, we have, okay, so we want to define yn. Yeah, okay. So straight, okay.
yes, sir.
Nissim, yeah, just wait. Nissim,
So Nishmin,
Nissim, yes.
a to the power n cos ax plus b plus n pi by 2.
A to the power n cos of
ax
plus
plus
b
b
plus
plus n pi by 2.
Great. Okay, so that's good. Okay, so here we got the nth derivative. Okay, so that's great. Okay, all of you are getting the same answer. Are you getting the same answer?
Yes, sir.
Yes, sir.
So if you are getting the
Yes,
same
sir.
answer, then please lower your hand. Okay, if you are getting something different, then we'll discuss. Are you getting the same answer? Yes, Pagare?
Yes, sir.
Okay. Jason, you are getting the same answer?
Yes, sir.
Okay,
Also,
so
do we have to simplify like for odd and even as
Yes, sir.
Do we do that?
yeah, that goes more. Now we don't know right now what is n, whether it is even or odd. Okay, so n can be anything. Okay, so just we are finding the nth derivative. N can be anything. N can be 15, n can be 20. Okay, so that's okay. So this is the nth derivative. Okay, so now as we are able to do for cosine, can we do it for sine? Okay, so let us think. Let us try. So are you done with this cosine?
Yes, sir.
Yes, sir.
Okay,
Sure,
that's great.
sure.
If you are done with the cosine, okay, then we can think of the sine. So let y is equal to, okay, so we have sine of ax plus b, where b the function of x. Okay, so if you are not able to read or understand anything, so please be frank to us. Okay, so now think of this. Okay, yeah. So think of this function. So what we do is differentiate. So differentiating y with respect to x, we get. Okay, that's great. So we'll have y1. What is the derivative we'll have for this sign?
Cos AX plus B.
Good. Okay. Is that sufficient? Cos ax plus b?
Into A.
No, sir.
Into
Into
A.
Cos AX plus B.
Yeah, the constant should be considered. Okay, so we need to be careful. Okay, once you miss the first step, okay, you are going to miss remaining all the steps, though you know. Okay, so it will be a into cos of ax plus b. Okay, is that okay?
Yes, sir.
Yeah. Okay. So now again we'll do a small exercise. Okay. So earlier we have considered for the cosine. Now consider for the sine. So what we'll be having? Sine A plus B. So we know this formula. So it is sine A cos B and plus you have cos A sine B. Is that okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Sir.
So again, what we'll do is put b is equal to pi by 2. Okay, so if we put b is equal to pi by 2, what we get here? Sine of a plus pi by 2. Okay, this is going to be sine a and cos pi by 2 plus this is going to be cos a and sine pi by 2. Okay, so what is the value of cos pi by 2?
0.
0.
Yes. So what will remain here? So this is 0 plus you'll be having cos A and into this, what is the value you will be getting for sine?
1.
1.
So this is going to be 1. Okay. So what you got here? Cos A. So that means whenever I have any term cos A, I can always write it as sine A plus pi by 2. Is that okay?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
This is the important formula that we have now. Okay, or which will help us to understand the derivative, nth derivative of this function. Okay, and hence now what I can write is y1 is equal to, can I write this as a sine of ax plus b plus pi by 2. Is that okay?
Yes, sir.
Yes, sir.
Okay, that's great. So we got this one. Okay. Now we go for the next. Okay, so we want to find its derivative again. Yeah. Okay. So once you are done, please mute yourself. Okay. So again, differentiating. Please mute yourself if you're done. Okay. So again, differentiating above equation we get. So what we are able to get? See, this will be y2. This a remains as it is. The derivative of sine is to be cosine. So it is cos of ax plus b plus pi by 2. And the coefficient of this term, again, you will be having this a. Okay. So what we get here, okay, is okay. So what is the derivative we got here? This is y2 is equal to a square cos of ax plus b plus pi by 2. Okay, so can we write it as y2 is equal to a square sine of ax plus b pi by 2 plus pi by 2. So can we write it like this?
Yes, sir.
Yes, sir.
Okay, that's great. So we got here y2 is equal to a square and we have sine of ax plus b plus 2 pi by 2. Okay, so as I said, don't be in hurry because we have to reach to the nth derivative. Okay, and we need to observe. Okay, so don't try to have the conclusion in a few steps. Okay, so we got here y2. Great. Okay, now think of y3 and y4. Okay, so what we'll do is again differentiate. Okay, so again differentiating above equation we get. Okay, so what we get here, this is going to be y3 a square a, and this is cos of ax plus b plus 2 pi by 2. Is that okay? Are you getting this?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so can we write y3 as a cube cos of, this is going to be ax plus b plus 2 pi by 2, or this is a cube and sine of ax plus b plus 3 pi by 2. Is that okay?
Yes, sir.
Yes, sir.
Okay, that's great. Okay, so we got the third derivative as a cube sine of ax plus b plus 3 pi by 2. Okay. Yes. Now we go for again derivative. Okay. Again differentiating above equation with respect to x we get. Okay. So what we are able to get, y4 is equal to, I'm writing now, let us check. So this is sine of x plus b plus 4 pi by 2. Is that okay?
Yes, sir.
All of you are getting this one?
Yes,
Yes, sir.
Yes, sir.
Okay. So I hope all of you have seen the superposition of waves in physics. Okay. All of you have studied waves in physics, no?
Yes, sir.
Yes, sir. In
Yes,
first
sir.
standard.
Superposition of
Yes,
waves
sir.
in physics, right? Okay, so
Yes, sir.
actually, this when we say cosine and sine, you can see these are the waves. Okay, and when we differentiate these waves, okay, so the derivative we are going to have, the derivative of the sine is going to be cosine, and the derivative of cosine is going to be sine. but we are trying to express in terms of itself. Okay, so the original wave, we are trying to find the relation between the tangential wave and the original wave. Okay, so what is going to be the tangential wave and what is going to be the original wave? So we are finding that when we are having a tangential wave, its magnitude is increasing. Okay, so this first term, okay, this first term is nothing but the magnitude. So its magnitude is increasing by the factor which is coefficient of x. Okay, so its magnitude is increasing by the factor of the coefficient of x, and its phase or its angle, its phase difference is going to be pi by 2. Okay, so we have two things, a magnitude and a phase difference. Okay, so the magnitude is every time it is going to be increased by the coefficient of x, and its phase is going to be shifted. So this is a phase shift. Okay, so phase will be shifted by an angle of pi by 2. Okay, so this is these are very interesting properties actually that you will also explore in coming semesters. Okay, so these are basic functions, but they have a tremendous good properties and applications. Okay, so here we got the first derivative, we got second derivative, we got third derivative, we got fourth derivative. So can we generalize the formula? Okay, so do you find any of the pattern in this four derivatives? So I want you to write it. Okay, and then let us check. Okay, so here we can have, and we can go on this, and then in general. Okay, so we have we want to find yn. I hope it's going to be easy for you to guess, and that is going to be yeah. I'll check. Dipesh, yes. Dipesh.
Sir, yn is equals to a raised to n sine ax plus b plus n pi by 2.
Yeah, that's good. So it is going to be sine ax plus b plus n pi by 2. Okay, that's good. That's what Dipesh said. So if your answer is same, then please lower your hand. Okay, if your answer is going to be different, then we can think over it. Okay, Shubhada, do you have the different answer?
No, sir, I forgot.
Okay, so your hand is raised, so that's why I thought you might be having the different answer. Okay,
No, but
okay,
I see my hand is lowered.
okay, 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 no problem. Fine. Great. Okay. So now, up to it, do you have any query or anything that you were not able to get?
No, sir.
Okay.
No, sir.
You got everything?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. That's great. So you can see we have been to the exponential function. We have been to the trigonometric function. Now you got the idea how to go for the higher order derivative and how to go for the derivative, nth order derivative, how to identify the pattern and how to extract the information from the fourth derivatives that we have calculated. Okay, see, if you know the formula, you can apply directly. Okay, but if you don't know the formula, then this is the way you need to derive. Okay, so if I will give you what is the nth derivative of sine 5x, then immediately you can apply this formula and done. Okay, but if you don't know how to find how the formula can be applied, then you just work out with the 4 steps. So nothing, you will get the same answer, but only thing is that the number of steps will be less or more. Okay, if you know the formula, then it is going to be easy that you are able to write it directly in the 2 steps. Okay, but if you don't know the formula, then you have to work out. Okay, nothing, and then in 2 minutes you are able to get the formula, or you are able to get the nth derivative, first derivative, second derivative, third derivative, fourth derivative. See the pattern, observe the pattern, replicate it, and then guess, yes, what is the general formula or what is going to be the nth derivative. Okay. So I hope everything is clear up to 8. You got
Yes, sir.
everything?
Yes, sir.
Great.
Yes, sir. Everything.
Yeah, great. Okay. Yeah. If you want to say anything, you are welcome.
Yes, sir. I just want to ask that which calculator we have to use for semester.
Okay. So good. Okay. So if you want to use the calculator, generally we prefer. Okay, just wait. Okay. I'll stop sharing the screen now. Okay.